All right, so we're ready to look at an abstract definition of a vector space. So here's our definition. We're starting with F is any field. So we have all those field properties: addition, multiplication, inverses for both, and all of that good stuff. And what we're defining is a vector space over F, which also is sometimes called an F vector space. And the vector space is the set V. So V is the set of vectors. V has to be an abelian group under addition. So I have to be able to add vectors. It's commutative, it's associative, there's an additive identity, all of that stuff. And then we have this function. And so this is our really abstract way of writing down what this function does. It takes an element from F, an element from V, so that means a scalar times a vector, and it produces a vector as output. So this is just scalar multiplication. We usually use a dot, a times. So if we think of R and S as scalars, and U and V, V and W, I've named them, as vectors, then we have a bunch of properties. So property 1 and 2 are both sort of distributive properties. They're distributing different things though. So notice that in the first one, this V plus W, that's a vector addition. In the second one, R plus S, that's scalar addition. So these are slightly different properties, but really it's just saying we can distribute. Okay. Number 3 is sort of an associative property. And again, there's subtlety here. So RS, that's just the two scalars multiplied together. Over here, the S V, that's a scalar times a vector. That's a scalar multiplication. And then that produces a vector, which we then multiply by another scalar. And so there's different stuff happening on both sides of those. And then the last one is talking about the scalar 1 is sort of an identity under the scalar multiplication. Okay, so V and W are the vectors, R and S are the scalars, and this is our definition of a vector space. All right, so let's look at some examples of these. So some are really familiar, and we looked at those in the last video. So let's talk about maybe R4 is an R vector space. And so when I say that, I'm telling you two things. I'm telling you that R, these are my scalars, and R4, these are my vectors. Okay, and so in this R4 as an F vector space, I might talk about this scalar multiplication as something like I can do -4 times the vector 1, 2, 3, 4, right? So, and I know how to add the vectors in R4 and all of that good stuff. So here, let me just write down my final. -4, -8, -12, -16 would be the product there. All right, so that's one that's pretty familiar, and I just picked R4 arbitrarily, R whatever you want to do as an R vector space. All right, one that is familiar but a little bit different. You don't usually think about this as vectors, but we can, is the set of complex numbers C is an R vector space. And so again, when I write that down, I'm telling you two things. These are the scalars. These are the vectors. Okay, so let's look at what calculations here look like. So if my vectors are elements of C, that means something like 1 plus 3i is a vector. Okay, and the scalars are real numbers, so something like 7 is a scalar. And I know how to multiply those. I know how to add vectors. I can add, for example, I could do 1 plus 3i, the vector, plus the vector 2 minus I, and I would get 3 plus 2i from it. And then I can take that scalar 7, and I know how to multiply it by any vector I want. So I would get 7 plus 21i. So this is maybe feels a little bit different, but it obeys all of those rules. I have addition over C. It's an abelian group over addition. and I have this scalar multiplication. I know how to multiply vectors from C by real numbers. All right, here's another one. So the set of 2 by 2 matrices with real number coefficients is an R vector space. Okay, so this time there's my scalars, R again, and these are my vectors. 2 by 2 matrices are my vectors. So my vectors now are matrices, 1, 2, 3, 4. We don't usually call those vectors, but it works in this setting. If we're thinking of this as a vector space, we can consider these to be our vectors. And I know how to add them, and it's an abelian group under addition, and I have all those good properties. And I know how to multiply matrices by scalars, by real numbers. So I can take, for example, -4 times my 1, 2, 3, 4. And I get -4, -8, -12, -16. This example should feel a little familiar. I did it before, basically, but instead of writing those 4 numbers, 1, 2, 3, 4, as a horizontal vector in R4, I've written it as a matrix. All right, let's see, I should probably add this just so it doesn't look incomplete. There we go. Okay, so that's another vector space. Here is another one. So Q adjoin root 2 is a Q vector space, a vector space over the rationals. Okay, so now again, I'm telling you these are my scalars and these are my vectors. So this time, my vectors, let's do a little vector addition problem here. So I might take 2 minus root 2 as one vector, and I can add to it 3 plus 4 root 2. And I know how to do that. The addition is abelian. It's an abelian group under addition. I get 5 plus 3 root 2. I have an additive identity. And then I also know how to multiply by scalars. So my scalars here are just rational numbers. So I can take, for example, my 2 minus root 2, and I can multiply it by 7. Okay, and when I do that, I get 14 minus 7 root 2. And that scalar multiplication, I can distribute, it's associative, all of those properties up at the top here are going to hold in that setting. So now you might suspect where I'm going a little bit with this, but in general, so in general, let's see, if F is any field if R is a ring that contains F, R is an F vector space. Okay, so if I have a small field and then I have a ring that's a little bit bigger that contains it, then that ring is an F vector space. So let's look at some more rings that contain fields that we've seen. So for example, Rx. This was, remember, the set of all polynomials with the variable f. This is an R vector space. Okay, so this time R, those are my scalars, and my polynomials are my vectors. And so if I'm talking about something like vector addition, then I'm talking about adding polynomials. 1 plus 2x plus x cubed plus 8 minus x to the 4th. And if I know how to add those, I know that it's an abelian group under addition. So what do I get? 9 plus 2x plus x cubed minus x to the fourth is my sum. Okay. And then I also have this scalar multiplication. I can take my 1 plus x cubed, or any polynomial I want, and multiply it by any real number I want. So I get 7, 14x plus 7x cubed. All right, and this obeys all the properties of a vector space. So let's look at those properties one more time. So when we have this setting of a ring over a field, then all of these are just kind of coming from the ring structure and the field structure. So all of this distributive property, if we're talking about rings and fields, these are all kind of the same operations that we're used to in the ring and the field. And we have that additive identity, everything's associative and distributive, and we have all the things we need to do this vector space interpretation of what's going on. All right, so where we're headed this in the next video is to try to explore our next ideas. So our next ideas are going to be related to how we think of R2 and R3 in terms of how big they are. So we talk about R2 as a two-dimensional space. Okay, and R3 is a three-dimensional space. So what we want to get an idea of is, what do we mean by that? What does 2 dimensions mean? What does 3 dimensions mean? And can we interpret that up here? What would we say about Rx in terms of its dimensions? What would we say about Q root 2 in terms of its dimensions? So you'll notice we've started talking about this already. How big are these spaces? This vector space framework is going to let us define that very precisely so that we know exactly what we mean.